Friends, I am Ghanshyam Jadhav. I think if you watch the 4 episodes on decoding the quantum mechanics, you won't forget, because through which I am to start a big debate. As you may know, the United Nations General Assembly declared that 2025 as the International Year of Quantum Science and Technology. It is believed that the framework of quantum mechanics was fully developed by 1925. Now it has completed 100 years. It is also believed that quantum mechanics is a remarkable mechanism that has proven helpful in developing advanced technology and explains what happens at the atomic level too. Currently, the aim is to build quantum computers that operate using qubits. We know that classical computers use 2 bits 0 and 1. In the world of quantum computing, these bits are called quantum bits or qubits, and they exist in the superposition states. It is also supposed that the advancement will increase computers' processing speed and their ability to manage qubits, allowing long calculations to be completed almost instantly. This is the primary image of one of the quantum computers launched by Google, which is currently under development. Global investment in the development of such computers is growing rapidly. It is estimated that it will exceed $55 billion by the end of 2025. China leads the way, then later the European Union, and next the America. Private players like Google, IBM, Microsoft are also in the race. Friends, to be honest, it is enough. I can't take it anymore because all the money belongs to the public and we must get to the bottom of whether anything can be achieved with it. Otherwise, all this money will slowly go down the drain and with it, our hard work too. Furthermore, future generation may call us as fools. So, my request to all of you and to anyone interested in this subject, no matter what, watch the 4 episodes related to decoding the quantum mechanics. Whatever you want to do afterwards, it's up to you. So first, let us see what is the base of the quantum mechanics. In fact, the basis of quantum mechanics is the wave-particle duality. It has two parts: particle nature of waves proposed by Einstein in 1905 to explain the photoelectric effect, and the wave nature of particles proposed by de Broglie in 1923 as a counterpart to the Einstein's hypothesis. In this context, I would like to quote what Albert Einstein said to his friend Besso in 1951. All these 50 years of conscious brooding have brought me no nearer to an answer to the question what of light quanta. Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. This means that Einstein was worried about light quanta. Perhaps he knew that light quanta was a trick used to solve the photoelectric effect, but something different might be happening there. So he was saying, look for that. But at that time, his position on quantum science was such that no one cared with him. Therefore, no one took that thing seriously. So the very foundation of quantum mechanics was being rejected by Einstein himself when, in his final days, we will explore why he felt this way in the first episode. After that, we will discuss whether a classical explanation of the photoelectric effect was possible or is possible. Because even though light is an electromagnetic wave, no one ever considered how its electromagnetic fields apply forces on electrons. This is a quite surprising trend. In the third episode, we will discuss what actually goes on inside the atom and whether today's understanding of it is right. And in the fourth episode, we will discuss the debates that arose as the framework of quantum mechanics was being developed, including what kind of debates and why. So, first let us look at how Einstein became involved in quantum mechanics. For this, we will have to probe into history of physics. Einstein had a girlfriend, Mary Mileva, whom he married on 6th January 1902.
Einstein probably wrote letters to her in the first 1 or 2 years of the 20th century. Three of them are particularly important as they illustrate Einstein's thinking about photoelectric effect. In one of them, written on 4th April 1901, he says, I have doubts about Max Planck's work on radiation, the fundamental wave nature of light. Therefore, I am reading this article with mixed feelings. Miss Einstein was complaining in the letters about the Max Planck's paper. In the next letter, just written 7 days after, on 10th April 1901, was still complaining about Max Planck's paper. Now it is important to see why Einstein was complaining. In the late 19th and early 20th centuries, three problems were being discussed: black body radiation, the photoelectric effect, and atomic structure with the emission and absorption of spectra by atoms, which classical mechanics could not explain. At that time, Max Planck, a German physicist, was working in thermodynamics. On 7th October 1900, Heinrich Rubens, an experimental physicist, came to Max Planck's house with his wife for a tea. It is believed that quantum mechanics was born on this day, means on 7th October 1900. During the discussion, Rubens told Planck that Wien's law only satisfies experimental data of black body radiation in the high frequency region. Planck hoped that Wien's law would satisfy the entire black body region. Means Rubens found that experimentally the Wien's law was satisfying the black body radiation in the high frequency region, while Max Planck was expecting that law should satisfy all the spectrum of the black body radiation. However, at that time there was also another law which was Rayleigh-Jean's law, and it satisfied the low frequency region of the black body radiation. So things were going differently. When Rubens left, Planck began calculations and calculated that if he restricts the energy released from the molecular oscillator in the hot body to a certain value, a complete theoretical formula could be derived. Thus, on that day, while deriving a theoretical formula for black body radiation, Max Planck assumed that a molecular oscillator in a hot body oscillates at frequency nu to take in or give out energy in the integral multiple of h nu, that is in the form of 0 h nu, 2 h nu, 3 h nu, 4 h nu, and so on, where h is a constant later known as Planck's constant. Planck called this packet of energy as a quantum of energy.
So for the first time, we know now energy was represented in terms of frequency, and because hot body radiates energy in the form of light waves, so the light wave must contain packets of energy that depended on the frequency of that light. This contradicts the wave nature of light, which is why Einstein was complaining about the Max Planck's paper. But Planck, while explaining the theoretical equation of black body radiation or theoretical theory of black body radiation, later too stated several times that the quantum of energy was merely a formal assumption or approximation used to derive a theoretical formula. His intention was not to revolutionize physics. He was a straightforward man. But later, an important event occurred that can be considered a turning point in the history of quantum science.
In the first week of May 1901, Einstein read another paper written by Mileva's old professor Philip Leonard, a German physicist. After that, he wrote a letter to Mileva on 28th May of 1901, in which he mentioned that, my dear kitten, I have just read a wonderful paper by Leonard on the generation of cathode rays by ultraviolet light. Under the influence of this beautiful piece, I am filled with such a happiness and joy that I absolutely must share with you. Now, what was in that paper that made Einstein so happy? In fact, Philip Leonard was studying the production of cathode rays and discovered that when ultraviolet light is thrown on a metal surface, cathode rays, which is the chemistry of electrons, is produced. This was actually the photoelectric effect which was first discovered. Henry Hertz in 1887.
We all know now the properties of the photoelectric effect. It's worth to remind once again. The study showed that for a metal there is a threshold frequency of light below which electrons are not ejected, but at that frequency or above electrons are ejected. Furthermore, the important thing, the kinetic energy of those ejected electrons was proportional to the frequency of the light and not on its intensity. As the light intensity increased, the number of electrons ejected from the metal surface per second increased, and this phenomena could not be explained by classical electrodynamics at that time. Why? Because everyone to this date, today also, is stuck on the idea that light is an electromagnetic wave and its energy should be increased by increasing the intensity of light. And this is what students are taught today also. But no one understands that since light is an electromagnetic wave, how can its field apply force on the electrons? Wow, what a story! How blind followers we have become. So Einstein understood from that paper the light must consist of energy packets as Planck had suggested. Now he was excited. Why? He can now theoretically prove that light waves are made of energy packets which contradicts their wave nature. This would be a revolutionary theory, so he was eager to prove it theoretically and independently. That is why he had mentioned in his letter to Mileva. In fact, Einstein knew that light was a wave-like. How did he came to believe that light could be a particle-like? This is quite surprising. 15 days ago, he was confident that light had only a wave nature. Now, how did he change his mind? That's a surprising thing. Einstein had a very sharp mind. Therefore, he should have to try to understand how the electromagnetic field of the light could exert force on electrons, but he didn't. Perhaps this was due to his age at that time. He was only 22 years. At that age, people are often very excited about their ideas.
But Max Planck wasn't enthusiastic about this. He always remembered that quantum energy was a formal hypothesis. That was the difference between Max Planck and Albert Einstein. Then Einstein came with a theoretical paper in 1905 with the title On Heuristic Point of View Concerning the Production and Transformation of Light in German Language. I don't know why it took 4 years to appear. In that paper, to prove the quantum nature of light, he used Wien's law and calculated the change in entropy when radiation of a particular frequency is transferred from one volume to the another. Similarly, he calculated the change in entropy when n molecules are transferred from the same volume. The two equations he found structurally identical, so he compared and calculated that the radiation contained in that volume of monochromatic frequency behaved like independent quantum of energies having energy values epsilon is equal to r by n into beta nu, where these three are constants, and this product produces h. So this equation reduces to epsilon is equal to h nu, where h is called Planck's constant. He called it as a light quantum. Since 1926, it has been called a photon because of Gilbert Lewis. Therefore, in the further discussion, instead of light quantum, we will use the more widely used term photon. Now, while explaining the ejection of electrons from a metal surface by incident of light of particular frequency, Einstein stated that the light contains photons of energy h nu as expected, which travels with light as a whole without division. When such a light falls on the metal surface, then one electron at the metal surface absorbs one photon at one time. This energy of the photon gets converted into kinetic energy of the electron, and the electron, if it is at a metal surface and ejecting perpendicular to the metal surface, it will be ejected with maximum kinetic energy. Of course, some part of the photon energy will be spent to release the electron from the metal surface, which is called work function of the metal. So the photoelectric effect equation becomes the total arc energy of the photon is equal to work function plus kinetic energy of the emitted electrons.
In fact, this paper was just a mathematical setup and it is not widely read and taught. But at the same time, you also know that Max Planck's paper on black body radiation is widely taught. But people think that Einstein's paper is an excellent theoretical paper that had explained a photoelectric effect from all sides. That's why he got the Nobel Prize in 1921 too. In this regard, I would like to note that any theory required certain assumptions which ultimately determine the direction of that theory and influence the resulting theory. Therefore, it is important to remember that a theory can be built based on personal preferences. When evaluating any theory, it is extremely important to examine the assumptions made before its theory. If we do not agree with these assumptions, then that theory has no value even if it is matches the experimental data. In the process of deriving the theory of light quanta, Einstein also made several assumptions and we may find out whether these were reasonable or not. People also believe that Einstein's paper was not intended to explain the photoelectric effect. However, looking at the history of letters, it is clear that reason for writing this paper was precisely the photoelectric effect, which Kathy Joseph explained in detail in his video script. You can see it also.
Let us now see whether the assumptions considered by Einstein while developing the theory of light quanta were right or wrong. First of all, Einstein knew that light is an electromagnetic wave, yet he assumed that the energy of the light wave could be focused or collected at a specific point. How is this possible? To concentrate the energy at a point would be to compress the or shrink the entire field of the light wave at that particular location, which is not possible. When an electron absorbs a photon, Einstein might have imagined that the size of that photon would be approximately equal to the size of the electron. We suppose that the size of an electron is less than 10 raised to minus 9 nanometers. Therefore, the size of the photon would naturally be the same. Now that photon is formed from the collapse of one light wave. Let us say it is formed from a blue light wave with a wavelength 500 nanometers. This means that approximately 10 raised to 7 electrons would fit within one wavelength of that light. Now that light wave is created by the transition of electron within an atom and it must contain at least some number of crates and troughs. This means that the total length of this wave may be equal to 10 times larger than the size of the electron or that of the photon. That is, if we were to fit 1 lakh electrons in a row in one slot, there would be a total of 1 lakh such slots in that wave. How such a wave, along with its electric and magnetic fields, can collapse into a single point to become a photon is beyond of our comprehension. And if all this were to happen right before our eyes, we wouldn't even believe our own eyes. Just because we cannot see light waves, it does not mean that we should believe anything. Now it has become a common practice to push anything under the name of quantum mechanics and why the light wave should collapse at a point. However, it is possible that a light wave can travel a long path without scattering its fields, such as the light waves emitted by a laser beam. In such a case, the strength of the electric and magnetic field can remain unchanged even after traveling a long distance before interacting with other elements. We should accept that the reason behind this phenomena deserve further discussion, but still, it is a wave causing oscillations in its field in space, which makes it impossible to concentrate the energy at a specific point. Thus, it's still impossible for any light wave to collapse at a single point. We must admit that Einstein was wrong in this thinking.
Not only this, for instance, let us accept the energy of light wave concentrate at a particular point which Einstein called a light quanta or photon. Now, what is the type of that energy? Is it a divine power? Actually, we thought that energy is simply as a divine power. And if it is a divine power, then it will do anything. No one can predict what it will do next. So, how can go with that energy? Actually, we understood two types of energies. One is the kinetic energy and another is the potential energy. When a body when a body comes in motion, we assume that it has a kinetic energy to understand impact when it collides on another one. Actually, a body has a kinetic energy means nothing is inserted in it. Simply that body is in motion. That's all. The body remains same whether it is at rest or it is in motion. Thus, the body has physical existence, but the kinetic energy does not have. Kinetic energy is simply a conceptual thing. Similarly, when we lift a body under the gravitational force, we assume that the work is done while lifting the body, which is said to be converted into potential energy of the body. This is the way to understand the tension of the gravity or pressure of the force of the gravity on that body. Increase in potential energy of the body does not mean that something inserted in the body. It also indicates that the potential energy does not have any physical existence. It is a conceptual thing. Then how a photon, which is assumed as an energy point, can have a separate physical existence? What could a photon be? No one can imagine its a physical structure or physical form.
Again, for instance, let us accept the physical existence of energy point as a photon. Einstein further says that in photoelectric effect, one electron can absorb total or partial energy of one photon at one time. Now the next question arises, how does the electron absorb that energy? The electron just a particle, so does it have any mechanism to absorb that photon? Or does the electron eat that photon? Here is showing we have no idea what we are accepting under pressure. We have lost our ability to think independently. Suppose an electron absorbs a photon completely or partially. What will do with that energy? Can the electron decide it? Einstein says that energy gets converted into kinetic energy of the electron. Why? What is the scientific reason behind this? We assume that in stars, mass is converted into light quanta or photons, which are also eligible to produce the photoelectric effect too. Why do not these photons get converted back into mass, and why does not the net mass of that electron increase? So, what type of energy gets converted into mass? Do we know? Okay, once again, assuming that the energy of photon is converted into kinetic energy of the electron. Now, in which direction then electron will go? Does the electron have a decision power, or is there any mechanism to decide its direction? Where it will go, here or here? In which direction?
People say that the electron goes in a random direction and we measure that it coming out perpendicular to the metal surface for the photoelectric field. Very good. Very, very good. Is that randomness acceptable? No, never. So why do we believe such flawed assumptions?
I would like to remind you of an effect described by Arthur Compton in 1923. He discovered that loosely bound electrons within atoms can escape by the impact of X-rays. Further, he found that the scattered X-rays have longer wavelengths, indicating lower energy photons. He explained the effect by applying principle of conservation of energy as well as conservation of momentum in this process. That result made him realize that X-rays act like billiard balls, which helped to confirm Einstein's light quantum hypothesis. However, the same conservation law are also applicable to the photoelectric effect too. However, Einstein used the law of conservation of energy only. If we apply conservation of momentum to the photoelectric effect, then after the absorption of the complete photon, the electron should move deeper into the metal in the direction of the photon's momentum, and then it's hard to say what will happen to this electron. But experimentally we find that all these electrons are escaping in direction opposite to the speed of light. This definitely indicates that someone is pulling these electrons out of the metal surface. Who is it? Do we know? Remember that light is an electromagnetic wave, so electric and magnetic fields can together exert a force on the electrons, but no one has yet thought about this issue, which may be a rare example in the history of physics. One more thing I would like to mention here is that Einstein had said that electrons can also absorb partial energy of photon, but partial energy of absorption is never observed in the absorption spectra atoms. Now, in atoms, when an electron jumps from higher energy level E3 to a lower energy level E3, it emits a photon of energy HF1. We assume that this electron will go back to the energy level E3 by absorbing a photon of the same energy. If Einstein was right about partial energy absorption, an electron can absorb the required energy from a higher energy photon and go back to the energy level E3, then a photon of remaining energy can be released in this process. But this has never been observed experimentally and nobody cares, right? Why?
Next, tell me what is the role of the electric charge of or electric field of the electron in Einstein's explanation of the photoelectric effect. Do you think that the charge or field of the electron has actually no role in the photoelectric effect? Hey friends, it must be there, but we still don't know. Einstein theory of light quanta is based on so many flawed things. So why shouldn't we rethink about it? Don't we have any right to know what is really going there at the position of the electron in the photoelectric field? Are we afraid of anyone? Do we think that what will happen to me if I think like this and it turns out to be wrong? Then it would be a matter of great shame. Friends, just imagine what the coming generation will think about us. They will call us as fools. If one person is called a fool, no matter, but it would be amazing if everyone was foolish, and that too not for a year or two, but for 100 or 200 years. Instead of researching in science, they will probably research on how we become so foolish. And what is more, we have even been awarded prizes too. Friends, this has gone too far. Come together on this matter. We will slowly examine where the mistakes are made. We are not competing with anyone. At that time, everyone wrote what they thought was right. If there is a mistake somewhere, that's fine. Someone will have to deal with it. We will try to do this together. Before the next episode, I have a request for all of you to explore how the electromagnetic field in a light wave can exert force on an electron in the photoelectric effect. Perhaps you will get to the right root of the photoelectric effect. We'll discuss this in the next episode. Thanks to all of you.